So how do we work our conservative forces into our relationships? So we're going to look at our non-conservative forces, and the work kinetic energy theorem. So we know that in realistic situations, non-conservative forces such as friction and air resistance are usually present. The total mechanical energy of the system, though, is not. So if we look at developing, how do we build in, NC stands for non-conservative, our non-conservative forces into this relationship? So by definition, if we look at the net amount of work, we already said that the grassroots equation here, 1/2 mv final squared minus 1/2 mv initial squared, is equal to kinetic energy final minus kinetic energy initial. So if we also look at our relationships then with work conservative and add the non-conservative to it, both the conservative and non-conservative, we end up with the same representative grassroots equations, 1/2 mv final, 1/2 mv initial squared. And we look at the relationships with potential energy. We have our same definition for kinetic or for conservative, potential energy initial minus potential energy final. To that, we can add our work non-conservative to just directly to that relationship, and we end up again with our definitions here: 1/2 mv final squared minus 1/2 mv initial squared, such that our non-conservative terms, 1/2 mv final squared minus 1/2 mv initial squared, are subtracted if we're dealing with potential energy from those terms. So we can say then that work non-conservative is equal to what we've seen before, the kinetic energy final minus the kinetic energy initial minus the potential energy initial minus the potential energy final. And so the next step then, all we're doing is, just as we did before, we're gathering our terms. So the non-conservative terms would be the final terms in the first parentheses, the initial terms in the second. So all the work done by all non-conservative forces equals the change in mechanical energy of the system. Okay, with that said, it's best just to look at the problems and see how it plays out. So in this case, we've got a crate sliding down a ramp, and you can see the depiction here. A 3-kilogram crate slides down a ramp at a loading dock. The ramp is 1 meter long and inclined at an angle of 30 degrees. The crate starts at rest at the top, experiences a constant frictional force of a magnitude of 5 newtons, and continues to move a short distance on the flat floor. Use energy methods to determine the speed of the crate when it reaches the bottom of the ramp. Okay? Change that to at rest. Okay, so we can look at the diagram here real quick and get a sense of, what's going on here. 5 meters off the ground, initial velocity 0. We have to start thinking about our frictional forces. Remember the mu k, and the frictional coefficient. So those are still in play, but we're going to look at them a little different. There are ways that we can use that to solve for our problems. Okay, so at the top, it's at 0. At some point, it starts sliding down. It has a distance of 1 meter to flow, and it achieves some velocity at the end. So we're given a 3-kilogram mass. We are given a frictional force of 5 newtons, okay? And we are given a height of 1/2 a meter, okay? So we're going to use energy methods to determine the speed of the crate when it reaches the bottom of the ramp. So let's look at what kinds of things we can deduce. The potential energy initial does not equal the kinetic energy final. And this really comes into play when we start taking friction into account. Friction makes it non-conservative. So all of the potential energy at the top is not going to be recouped as kinetic energy at the bottom because some of it is going to be given up to friction. So the potential energy initial will still equal mgy initial. So we can calculate that. So 3 kilograms for the box, 9.8 meters per second squared for the acceleration of gravity, and 0.5 meter gives us the potential energy at the top of 14.7 joules. Now let's calculate our non-conservative term. Well, our non-conservative term here is minus Fs, okay? That's the frictional force in the opposite direction. You know, it's trying to pull the box back up the ramp, minus 5 newtons times the distance. We're going to use S in here instead of X. So we have minus 5 times 1 gives us a minus 5 joules. So you can see the non-conservative force is taking away from the conservative force. So minus Fs then we set equal to 1/2 mv final squared minus mgy. And we're going to move terms around here because we're trying to solve for the velocity. We can calculate our final velocity out of this. So let's move that term around. 1/2 mv final squared is equal to mgy initial minus the frictional force Fs. So let's put our terms on this side. So we've already calculated mgy as 14.7, and we've already calculated F times S as 5 joules. So now when we subtract one from the other, we get 9.7 joules then is going to be the kinetic energy at the bottom, of which we can extract our final velocity. So now moving terms around, velocity final squared is equal to 2 times, because we're going to move that 2 out of the denominator, mgy minus Fs divided by m, the mass. So we get 2 times 14.7 joules minus 5 joules divided by 3 kilograms. We get V final then equal to 2.54 meters per second. So you can see this non-conservative force becomes the friction, and it just becomes things acting in the opposite direction. The next one, they say find the speed at the bottom of the ramp if the ramp surface is frictionless. So now we're going to take the friction away and see what the difference is. Here we had 2.54 meters per second. So now using the same things but no Fs, we run it through the relationships knowing that we have an initial velocity of 0 and a final height of 0. When we plug our values in, our 0 terms disappear. We're left with 14.7 joules is equal to 1/2 3 kilograms times velocity final squared. Move the velocity final squared to the other side of the equation by itself. Take the square root of 9.8 meters squared per second squared, and we get now 3.13 meters per second as our velocity. So you can see if we discount and take the friction away, it certainly is going to increase the velocity. Okay, so when we come back, we'll take another look at this. This is kind of like the diver problem, but we're going to add friction in and out of the relationship.